Hello, everyone. This is Spencer Snowling from Hatch, and I'd like to welcome you today to our regular GPS.X webinar. Today, we're going to be talking about using GPS.X for economic analysis of biosolids management at your treatment facility. So the idea behind this webinar is that I wanted to show how you can use the models to estimate not only the costs of operating your biosolids program, but also estimate the potential revenues and sources of being able to offset costs. And then to be able to balance those against each other and look for opportunities to understand better and to optimize your facility. So we're going to be doing some examples of those today. So as per usual, if you have any questions that come up during the webinar, you can go to your GoToWebinar dashboard and open up the questions panel and type your question in there. I'll just let those collect as we move along through the webinar. And then at the end, I'll stay and answer as many of those as I can. Okay, so my agenda for today is to first just give a little bit of background and context about biosolids management options at water resource recovery facilities. And so I'll talk a little about the technologies and various places that we can make some assumptions about costs and potential revenues. And then in order to be able to study those and do some sort of analysis, you're going to want to be able to set those up in GPS.X. So I'm going to spend a big chunk of the middle of the webinar talking about all of the various places that you need to be able to get access to set various operating costs and to generate information out of the model in terms of how much energy could be recovered, for example. So I'm going to go through a number of the different objects in the biosolids handling section of the software. Then I want to show how you can use sensitivity analysis to do an economic analysis and a bit of an optimization. And I'm going to do that by showing you two desktop examples today. And then, of course, conclude things. And then, as I mentioned earlier, if you have any questions, I'll stay at the end and answer those to the best of my ability. All right, so to kick things off, of course, the activated sludge process, as you all know, produces biosolids, or as we have used to call it in the old days, sludge. I'm sure the word sludge will probably get used a few times here. I still tend to sometimes refer to it that way myself. These solids need to be removed from the system in one way or another. They're often treated through physical, chemical, and biological processes prior to being removed from this facility. So that's done for a number of different reasons. Those being that you, first of all, want to be able to reduce the amount of biosolids that you are going to be hauling away from your facility. That is due to the cost. You want to get as much of the water out of it as you can and reduce the amount of actual solids that are there to be hauled away, to get the VSS reduction as much as you can. By doing that in an anaerobic context, you can generate some gas. So that might be one of your objectives as well, is to capture that gas and use it to do heating or generate electricity or what have you. A lot of facilities have the ability to recover nutrients, recover nitrogen or phosphorus, and then use those, sell those, particularly phosphorus being sold for the purposes of fertilizer, or to produce a reliable agricultural land application product. So if land application is where your solids are going to go, you might want to operate and optimize your biosolids treatment facility in a certain way in order to generate that amount of material and have it be disinfected by having a certain length of time and temperature and so on. So these are all things that you can model in different ways. And so we want to be able to use this, the powerful tool that is GPS.X, to be able to analyze all of this material. Okay, so for a conventional activated sludge plant, you, of course, are used to modeling the liquid side. And so, I'm hoping you've had a chance in the past to also model the biosolids handling aspect of your facility. And so the amount of solids that you're going to be treating on this side of the plant is a function of actually many, many different things. So it's a function of the way your plant is being operated. Like, for example, the SRT of the plant, you'll have different solids depending on whether you're running it short or long SRT, whether you're doing BioP removal or chemical phosphorus removal. If you add a lot of chemicals, you might end up producing more sludge. The biodegradability of the influent. If you suddenly had a large amount of inert material coming into your plant, that might make its way to producing more biosolids for you to have to deal with, and so on. So these are all parts of what we want to be able to optimize with our modeling technology. So typically in a conventional activated sludge plant, you're going to take the sludge that is being, or biosolids that is being wasted from your clarifiers, your primary clarifier and your secondary clarifier, and combine that. And typically you would be, of course, putting that in a thickener. Here I'm showing a gravity thickener, but it could also be other technologies, belt filter presses or what have you. And then that is then taken to the digester, digested, and then those digested solids would then be dewatered, and then the solids taken and hauled away to be disposed of in one manner or another. So the way that you use these treated biosolids really varies from plant to plant. And so the ability for people to do different kinds of treatment really is based on the available technological options, this quantity of solids that you're producing and the location and often the size of the facility itself. Some places have lots of agricultural materials and opportunities to be able to provide a product nearby. If you're maybe located where that is not an option, then that might not be economically viable for you. So many smaller facilities do not treat their own biosolids on site and then instead just store them. And that, of course, has its own cost. They store those biosolids and then they are transported to larger nearby facilities that are more likely to have a full biosolids treatment section. So I was looking around this week as I was setting up for the webinar, and I did read up a bit here, and I got a good estimate here on the amount of biosolids that are treated across the U.S. 4.75 million metric tons per year are being treated across 2,200 facilities. So certainly knowing that there's a lot more than that, a number of facilities out there, certainly a lot that don't have their own biosolids management, but certainly getting upwards of 5 million metric tons per year. It's a significant amount of material to be treated. Okay, so what are the options and what are the different things that you can do as part of your biosolids management program? So clearly, one of the options is if you have an anaerobic digester and you are producing a significant amount of methane gas, you can take that methane and then use that in a cogeneration plant. So you have the ability to potentially capture that gas and sell it back to a grid, for example, or you could burn it and you could make some heat, or you could make some energy from that, generate some electricity. And there's lots of technologies out there on the market to be able to capture both heat and power, CHP units, from various types of companies that produce this technology. I got a couple of pictures here. This is a CHP unit at Deerdykes in Scottish Water. So this was a facility that I believe not only treated their own waste, but also accepted a lot of food waste from outside. And this unit here, with the big globe behind it, methane storage tank. This is here at Woodward Avenue Treatment Plant in Hamilton, Ontario, where I live. This is a cogeneration unit that allows for actually some flexibility about whether it treats the gas or whether it actually uses the gas within the facility. So you can basically offset some of your own energy needs, or if you have excess energy, you could sell that back to the grid. So there's also options for nutrient recovery. So there are a number of technologies out there to precipitate out struvite and other forms of phosphorus, and then recover those for use as fertilizers or potentially other products. And then there is an opportunity as well to generate some income by receiving high strength wastes. So typically fog, from restaurant or food processing waste that you might have from, food processing facilities in your area, or any other kinds of other industrial waste. Sometimes these can be challenging things. There's usually extremely high concentrations that would go generally, for the most part, right into your digester. And so, but of course, you can charge for those. They call them tipping fees, charge money to be able to take that waste and treat them. And then, of course, you get extra gas because you're now taking all that in and generating a bit of electricity that way. Okay, so all of those things are generating money or offsetting costs that you have within the plant if you're using your own energy that you're generating rather than buying some off the grid, or if you have excess, selling it back. So those are positives. But at the same time, you have costs as well. So whatever you've got left over at the end of all of your biosolids treatment, you still have to do something with that and get rid of it, right? So typically that's land application or land filling or incineration. There are actually a number of plants here in Southern Ontario that do incineration of their sludge. There's also other things, surface disposal, storage, deep well injection, that kind of stuff. I found this really nice graph here in at the EPA government website that kind of told the story here that, a little more than half of all the facilities that are treating their biosolids are actually land applying it, and that's actually quite common. Okay, so all of those things cost money to be able to do that, right? It costs money to landfill your grit and your sludge. And on top of that, that's just trying to take the balance of all of the mass of the organics that you have. It also costs money to actually operate all of this too. So it costs their energy requirements for, mixing your digesters, potentially having to heat your digesters or other situations. Also pumping the sludge and moving it around and so on. And then also chemical costs, right? So almost all of these systems are going to have some sort of polymer dosage for doing better dewatering, and then potentially you may have to also add some sodium hydroxide or such to be able to control the pH and keep it from getting too low, for example. So we have a bunch of potential revenue generation, so that's a plus, and then we have a number of different kinds of costs, which is a minus. And so what we want to be able to do is use a tool like GPS.X to balance those things one against another and see what the overall net operation is. And that can be done actually at the design level by choosing different types of process configurations and using different technologies to figure out what is the best for your particular situation. So if you're building a new greenfield facility, or if you're upgrading or replacing the biosolids handling section of an existing wastewater treatment plant, you could look at doing various different types of options, and you could model all of those, such as this, typically conventional, thickener, digester, dewatering option, or maybe you might include a THP unit in here, thermal hydrolysis process. This is something that will take the thickened sludge, break it down, undergo hydrolysis, make it more readily biodegradable, and then put that in the digester with the hopes that you get a little bit better gas production. So those are things that you could evaluate. Or maybe you are going to do the conventional route and then actually take that sludge and dry it and then incinerate it as well. So that's another option that you could model. Or you could go the full-on nutrient recovery method here. So take your digested sludge, dewater it, solids get hauled away, and the centrate would come over here and go into this struvite precipitation unit, and you would be looking to remove the phosphorus and recover that, and then take and sell that as fertilizer. So there's 4 different options that you could model all of these and then compare them one against another to try and optimize and make the best selection. You can also do all this kind of modeling too at the operations level. So really to assess the revenue and cost balance for various operations and various loading conditions. And that's what we're going to do today. So most of the rest of this webinar is going to be focusing really on an operations side. And so that is going to say, how much of our flow should we be putting in the digester? How much food waste can we accept? Those kinds of things. So, and as always, I really enjoy using sensitivity analysis to be able to help, find that understanding of the balance of the costs and the potential revenues. And so that's what we're going to be looking at doing today here, finding the balance of treatment and disposal and cogeneration operations. Okay, so now to be able to do all of this, you need to be able to set it up and associate the appropriate costs that you want to capture in your model and the appropriate potential revenue generation units also in your model as well, so that you can put those two things together and subtract one from the other and find out whether you're paying or losing money, right? So basically, we're going to go through all of these units here in the biosolids treatment panel. So if you have GPS.X open and you got the white drawing board up there, this would be the panel to the left. You just click on biosolids treatment. And I'm going to run through all of these here fairly quickly, just describing where you would find all of the details to be able to associate the costs appropriately. So we have solid separation units here. So for example, your thickener, your dewatering unit. For those who might not be familiar, this is a sort of a generic black and blue box solid separation unit. That's kind of there to cover off many different kinds of dewatering technologies. Microscreens, hydrocyclone for solid separation, etc. So we also have the THP and chemical pretreatment objects for doing sludge pretreatment. We have our digesters, both aerobic and anaerobic. We have our phosphorus recovery units here for doing struvite recovery, and then sort of that post-treatment drying and incineration units. Okay, I'm going to be going through some detail here. I'm going to be focusing mostly on operating cost. However, I'd like to refer you over to the excellent webinar that we did last summer on modeling biosolids handling and side stream processes with GPS.X. And so you can find that by going to our YouTube channel, youtube.com/hydromantis, and you can find and watch that. And we did basically this entire list in much more detail than I will be able to do today. Okay, so let me run through several of these, and I'm trying to cover off like sort of all of the different ways that I think you might need to know about where to set up these costs. So in our gravity thickener model here, this is either an empiric model where you specify the percent capture, or it's the simple 1D model, which is the full 10-layer settler model, but with a different default settling calibration because it's sludge and you're doing thickening. It basically includes energy and disposal costs, as many of these objects do. And so you'll find an opportunity if you go to the operating cost menu, the input parameters operating cost menu, you'll find all these details here where you would enter in stuff about the energy usage, pumping of the sludge. And then here at the very bottom of that menu, the miscellaneous other power use, you know, so for like rakes or arms or whatever, and then sludge disposal cost, which you may choose to associate with this object, or maybe you're going to send it off to the truck and you can associate the cost over there. So just very quickly, I'll just show you what that looks like here. Here's a gravity thickener. And you can see that if I go here, input parameters, operating cost, and you can see that there's a lot of detail here about the pumping. There's two different pump connection points on that. And then here's that stuff at the bottom. You can see we've got that there. And then if I go to right click, go to output variables, again, at the bottom, it's usually at the bottom of the menu for most of the objects, click on operating cost. These are the kinds of things that you can plot. So anything requiring energy will tell you the instantaneous power usage, so in kilowatt hours. Then we integrate that over time so you can get the amount of energy required. And then we also integrate the number of dollars by multiplying instantaneously all the way along the amount of kilowatt hours used times whatever the price was at that moment in time. And then, so if you run a 5-day simulation, you can say this many dollars were used in that simulation. Okay, so I showed you that already. Okay, moving onwards, process from the thickener to the digester. So the digester model is basically a fully active biological model. It's a completely mixed reactor with a headspace. So it has the full Mantis 2 biological model in it with all of its anaerobic sections in there. So we got 3 or 4 biomass types that are there doing that digestion. And you can actually plot all of the details that you would normally be able to plot in any of our other biotanks. So you can see the specific growth of the methanogens if you want to, for example. So it's the full model. It's the full gas mass transfer. So as we're generating methane in the liquid, that will then transfer to the headspace, and we model that headspace concentration and pressure. And then several versions of GPS.X ago, we added this heat loss model and heat energy recovery model from a combined heat and power unit. that allows us to sort of do a lot of this analysis that I'm going to be doing today. It was previously a part of our greenhouse gas and carbon footprint model, but it was so useful that we actually moved it over to the regular Mantis 2 library as well. Okay, so there's all of those there, and you'll notice that in addition to the regular operating cost model, you'll find these extra ones there: digester heating requirement and energy recovery options. In the digester heating section, because we're doing a heat balance here, we want to know the details about how the digester is constructed so that we can figure out how much heat is going to be lost through the walls and the floor and the roof, et cetera, et cetera. So you have to enter those. And then once we do that and we do our heat balance, we can then determine in the end, do you have ultimately a conversion of that methane into some sort of energy? And then you can figure out how much that would be. These are all the different operating options. So you can put some of it to burning it for a boiler, some of it going to the combined heat and power unit, and you can flare some of it. Choose whatever you like there. And then we calculate that. And I won't go into a lot of details here, but you can see that almost all these cases, the boiler heat is just a function of ultimately of the gas generation. So it is the CHP heat, and also the electrical generation is just linearly a function of the amount of gas that's being generated. Okay, so once all of that is done, and we've got the amount that's being generated, and we figured out how much biological activity is going on and so on, and we got that heat balance model, we can then figure out whether you have a heat deficit and that you require some extra heating to be able to run this, or whether you're actually generating extra heat. And then that way you can use that and capture it. And then also, this is one of the most important ones for what we're doing today, is being able to, what is the estimate of the electricity generated from that system? Okay. Next step down the list. So now there's other assorted solid separation units for doing dewatering, microscreening, hydrocyclone, et cetera, et cetera. These are all there. They almost all of them have exactly the same kind of setup where you can specify energy usage and your disposal costs. So wherever the solids are going, you can associate that and figure out what cost you might want to associate there. Now, I'm also just going to take 1 second here to let you know that there's a new version of GPS.X coming, version 8.5, that will be out later this year. And I thought I'd give you a little spoiler that it's going to have 3 new biosolids handling units in it: a centrifuge, a belt filter press, and a gravity belt thickener. And so all of those will be also working kind of the same way that these ones do. These ones are just calibrated more specifically for each of these individual technologies. So previously, where you were using this generic block, you can probably use one of these going forward. And you'll also have access to the same kind of menu. Okay, so moving on to the nutrient recovery section, struvite recovery. Basically, it's going to have its own operating cost in terms of energy. There's some pumping and recycling and so on. This is a good opportunity to mention, though, however, you may have a chemical cost associated with this. So in the same way that if I go back here, this dewatering unit would probably have a chemical cost for polymer dosage in here. This one is different. This one here, you may need to be adding magnesium in order to be able to precipitate out the struvite properly. And that's not done within this unit. It's actually its own unit. This is part of the alkali dosage section. That's where you could set it up to use magnesium hydroxide in order to supply magnesium for the precipitation of struvite. But that's its own thing. So that'll be somewhere else on your drawing board, and you'll connect it up through a combiner and so on. And the chemical cost, the amount of money that you're spending on this chemical, will actually be associated with this unit, not with the struvite recovery, even though you're adding it because it's needed over here. So just wanted to make sure that that was clear, that your chemical costs are associated with the chemical dosage point. And then just like everything else, just like the energy ones, you specify a cost of that particular chemical. Last version of GPS.X, we updated all of our costs so they were up to the present, and as we usually do. And then here you can see, for example, the alkali dosage cost, $2 a day for this little plant exercise that I was running yesterday. Okay, so lastly, sludge drying and incineration. So these two units here, particularly the incinerator, has quite a long, lengthy list of operating costs. It's actually quite a long, detailed model too. It's a really interesting one to use. You can, if you open up the incinerator menu just for operation, you can see that there's fuel being sent and there's sort of heat loss and so on. And because of that, there is an energy balance going on here that we want to be able to calculate. And then from that, we can calculate a number of different kinds of operating costs, not only from the actual process itself and fans and blowers and so on, the actual cost associated with the fuel here as well. So in fact, it's such a long thing, I could barely squeeze it all on the PowerPoint slide here. Also, disposal and costs would be coming out of here as well. So this is basically your sort of your ash disposal that would come from the very, very end of the process. Okay, so I will mention again that we also did another webinar on this 2 summers ago on the sludge drying and incineration objects. And so my colleague Rajiv went through all of this in detail. If you'd like to know more about how those work, I recommend popping over to our YouTube channel to find out. Okay, and lastly, there is the sludge haulage truck. It is basically not required to do it. It is basically here to put some flow into such that you can then calculate a separate disposal cost for it. I find it useful for this particular situation, which is when you have multiple dewatering units that have their own separate costs and whatever for haulage, say, for example. But you ultimately, in the end, need to add it all up together. So you're going to run these 2 sets of dewatered biosolids through a combiner and into the truck. The combiner itself is not going to have a menu for disposal costs, but anything you put into a truck will. So if you have multiple solids handling streams and you want to associate it one single cost at the end of all of it because it's all being hauled away and costed the same way, then you can just put whatever combiners you need, combine it all together, and then stick it in the truck. And then inside the truck, there's a cost that you can dispose with it in terms of dollars per dry ton, for example. So that allows you to have a little bit of flexibility. You can associate it with the unit itself. Often that is actually dollars per meter cubed or dollars per volume, whereas this cost is in dollars per mass. So whatever way you want to do it is fine. You could do both. Whatever works for the way that you want to do your evaluation. You have those options available to you in GPS.X. Excuse me one moment. Okay. All right, so now I want to touch on 2 more things. These are 2 other things that are relevant to setting up your biosolids economic analysis, but they're not found in the biosolids section. They're actually found in other parts of GPS.X. The first one is setting up an influent to represent the food waste that you might be bringing into to put in your digester and make some money off of doing that. So what you need to do is you want to characterize the fog or industrial waste or food processing waste from the winery or brewery or meat processing or wherever it's coming from. You need to be able to set that up. And you can use the regular GPS.X influent object for that. The thing that is important to keep in mind is that you're going to be entering in typically, very high concentrations. And when you use Influent Advisor, you may recall that we flag any sort of problematic data as you're entering it, and you need to potentially change some of the other ratios farther down the menu in order to sort of help get the characterization all sorted out, make sure there's no negative concentrations. So you can see here, typically for something like fog, this is going to be a huge number, hundreds of thousands of milligrams per liter of COD. And so that's also potentially going to require, fairly large concentrations of nutrients. And that's going to cause you to have to move away from our standard ratios and stoichiometry that we would have down here. Now, these are all set up by default for regular municipal wastewater. So when you start entering numbers like this, will need to be changed. These are not representative of food waste at all. So please feel free to go and change these as required. You may also find that a little farther down that menu, you need to change these N and P, these nutrient contents of this really huge number here. This is often, sometimes you even have to set them to zero. Doesn't mean you don't have N and P in your food waste. It just means it's not that much associated with the inert material. So I've done a couple of projects, or many projects actually, over the years. And one thing I'd really like to hit on, and when you do the GPS.X training, I always come back and hit on this point many times. When you get into characterizing a food waste or an industrial wastewater, like basically all bets are off. Like it's going to be different for every site. It's very, very site dependent. Every particular industry has a really different kind of mixture of things that come to make their wastewater. And so I've had the luck and opportunity to model a bunch of different types of industries, and they're all over the map. So we did a project quite a few years ago that had a facility that was producing corn syrup. And so the wastewater that was coming to the plant was being accepted and taken in. It was really high concentrations of COD with practically no nutrients at all. And then I've also worked on like meat processing facilities with huge concentrations of ammonia and not that much COD. So, I mean, it's still more than regular wastewater, but like in the relative proportion of COD to N was like completely flipped the other way. So you need to make sure that you've really got a good amount of data on what your food waste is coming in. Did a project a number of years ago too with winery waste that was being brought to a relatively small plant actually, but it was a huge loading. And we did some modeling to help them confirm that it should be put into the digester rather than into their headworks. So that was quite an interesting project to work on. Okay, and the very last thing that I want to mention is setting the energy cost. What is the dollars per kilowatt hour, for example? So the energy price is actually set in the site properties menu. It's this little pin button in the upper left-hand corner of your drawing board, and it opens up this menu. You may have come here before to maybe set your simulation time or adjust the plant-wide properties where you set the plant temperature and elevation and whatnot. The very far right, energy cost here. And you can set either a constant price or a time-based price, such that you can have it so that energy is cheaper at night than it is during the day, or seasonal-based pricing. And that one's really quite elaborate. The menu goes on for quite a bit here, where you can just say that in the summer it's one price, and in the winter it's another price, and maybe it's different on the weekend than it is during the day, et cetera, et cetera. So we've got lots and lots of options in controlling the price. But basically all it does is, in the end, set dollars per kilowatt hour. Okay, so that's a whole lot of information. Basically, I just want to bring it back to say all we're trying to do here is model a single plant, capture all of the costs so that we can balance them versus either the offsets of the energy requirement or actual revenue that we're going to bring in for this facility. And so you want to play one during the other. And of course, it depends on what you're trying to do with your facility. I mean, not every facility needs to run at a profit. It's just this is a nice way to manage and understand where you are at. Okay, an awful lot of talking. Now let's get to actual simulating. So here we go. So this is a plant. Oh, sorry, I jumped off of the slides one too soon. I wanted to use this slide to just very quickly explain what we're looking at here. So now I'm not modeling a whole plant. We're just modeling the biosolids part of it. And we have a couple of influents here that represent our primary sludge and our waste activated sludge. We also have another influent that has been characterized for the fat, oil, and grease for the fog coming in. And this actually has a relatively low pH as well. And so that previous menu that I showed you the screenshot of is the characterization of this waste. And then we also have the ability to split flows. So the primary sludge can be taken through this gravity thickener, and then it can either go and be dewatered and go straight to landfill, or we can split the flow, go through the digester, digest it, get some gas production, dewater the remaining sludge, and then land apply it as a product. So these are going to have different costs. This kind of endpoint and this kind of application are going to have different costs associated with them, and we can split them evenly or put it all one way or put it all the other way. And again, same thing with the WAS. We can thicken it and we can send it all to be landfilled, or we can send it through the digester and out to be land applied. And the fog by default is going to go in the digester and then dewatered and taken for land application. And as I mentioned, we have some alkalinity dosage here to help us with pH issues. Now, in a regular plant, we would also probably recycle from all of these overflows of the gravity thickener and from the centrate and so on. That would all go back to the head of the plant. Not showing that in this particular model, but if you did a model of the whole full plant, you had the opportunity to see what effects this operation would have upstream as well. Okay, example number 1. We're going to do a co-digestion sensitivity analysis. So basically, the question we want to answer is how much food waste can we accept into this facility? And that's going to bring us some revenue through a waste tipping fee. And it's also going to bring us some biogas revenue because that, of course, is going to produce more gas. And we are going to generate electricity, which is then to be sold back to the grid. One of many options of different things that happen in various facilities. And we picked this particular example to be set up that way. Right. Okay. So here we go. I'm going to go over to simulation mode. And as I always like to do, I want to use our analyzer function to be able to get a good understanding of what's going on at this facility. So here's the model that I showed you earlier. If I go to the digester page here, you can see that this fog influent, which is this food waste coming in here, going to go right in the digester, dewatered, and out for land application. And all of the costs that we're going to be having are all being calculated all the time. Now I'm going to turn on this analyze mode, and this is the analyzed parameter that we're adjusting, which is that flow rate from 0 meters cubed per day up to 60 meters cubed per day. And I'm going to just do a regular steady state analysis here. So this, if you haven't seen our analyzer function before, what's happening is it's running a series of steady state solutions to the model. All the other parameters are being held the same. However, this thing is being increased on every run. And so we're doing about 15 runs here. And so, oh, you know what? I'm in the wrong scenario. Pardon me. Hang on. Got to go over to the cogeneration scenario. There we go. Let's try that again. Okay, so we're running through all the way here through the co-digestion scenario, and we can see that as we accept more waste, it's causing a number of things to happen. So let's just take a real quick look here. We can see as we're bringing more waste in, the steady state solution, as if the facility has been running for a few weeks with this level of waste being accepted. We can see that the pH is kind of coming down here a little bit. So it was set up such that we had 7.3 pH with no fog coming in. But as we accept more and more, it's going to come down and drop below 7 there. We can also see that we have some food waste tipping fees that are coming in. So the more we bring in, the more money we make. And also this biogas production goes up because we're now generating more gas from the larger amount of waste that we are digesting at the facility. Okay, so what happened here now, as you can see, is that we've kind of dropped off the table a little bit. So what's happening is that we've kind of reached the point at which the facility is sort of maxed out with what we can do with the digester. And suddenly it all went sour and the pH dropped quite a bit. Now, I've put these all on a graph that's a little bit more well organized here. So basically, that simulation I just ran, these are all the results. And it tells that story that, you know, as we were accepting more food waste, we were bringing in more tipping fees up until the point at which we overloaded the digester. So if we look at gas production, you can see at that same point when suddenly the pH dropped and we were now inhibiting the methanogens, and so we're not producing any gas, or producing a lot less gas. So we can see that this is kind of the tipping point, right? So that is also here, the heat and electricity generated from this biogas, and our biogas revenue kind of drops right off. Our food waste tipping fee was 0 at the beginning when we're not accepting any, and it's just a linear relationship. And then if you add this revenue plus this revenue, and then subtract out all of the various costs, like as we were producing more biosolids, we needed to spend more on polymer for keeping the dewatering in good shape. And of course, more biosolids means at the end, you had to still land apply more, and that costs some money. In the end here, we can do a net revenue. So this includes these numbers plus a whole bunch of other costs and revenues. And you can see here down at the low end, it's probably actually a net loss. But as we're bringing in those tipping fees, we can kind of get up into a positive. And then, of course, this point right here is sort of our optimal. Now, of course, you wouldn't want to operate right on that top, but somewhere down here where you can say we're safely using all of our digester capacity and we're generating as much as we can, and that's good. So, and it's really this pH drop that's sort of defining where that maximum point is. Okay, so now what if we were to use some caustic, some NaOH here to kind of help this pH problem? So I'm going to put in 1,500 liters per day here. And I am going to now rerun that simulation. And we're going to do that simulation over again. And basically, we can now see that we started out at a slightly higher spot because actually, even though we didn't need it, we're just to make things easy to explain, we're leaving the caustic dosage on all the time, no matter what a constant amount, no matter what was being added to the digester. And again, it's doing its steady state solution as we move through here. So the hope is, of course, that as we move along, we can get farther along here before it drops off. And, we can basically increase the capacity of our digester and get some extra gas over here where we couldn't get that before by dosing some chemicals to help with the pH issue. Okay, it's taken a little while, but you know what? I've actually got a nice graph set up here that kind of tells the story. So I'm just going to, while this is chugging along, I'm going to show you the end result because I wanted to compare the previous run versus this run together. All right, should I just let it go? It's going to happen over here. And come on, solving these models is a little challenging. The digester model's got a lot going on in it. So, and anyway, I'm going to show you what it looks like. Oh, there it goes. Okay, so we can see that it did drop off just like it did previously. But now, instead of over here at like 45, where it was previously, it's actually more like 55. So, so let me show you the slide where I've got the previous run here, the pH and the net revenue, and then the red run is the one that I just did. So with the alkalinity dosing turned on. So you can see immediately, we started out above where we were before, and we got a little bit more mileage out of this here. We can accept another 5 to 10 meters cubed per day of fog because we're managing the pH a little better. But now let's look at the net revenue. Well, it starts out, and because we're dosing all that chemical, where it's an extra cost, right? So that means it kind of moves things over. And the really interesting aspect is, even though we've moved this operating point up here, and we're now accepting more waste and generating more gas, ultimately, it gave us a smaller amount of net revenue because the cost of doing the dosing more than offset the gain that we got from the higher amount of tipping fees. So it's a really interesting thing to play around with. And of course, this is a hypothetical example, and there's lots of things at play here. We could operate the digester differently. Maybe we would want to move a little bit between one of the other options for landfilling or land applying, or operate the digester at a little warmer temperature. Who knows? Any of those things can be analyzed by doing this kind of analysis. But I think hopefully I gave you that flavor of this is the kind of thing you can do with the model where you've got 6 or 7 positives and 6 or 7 negatives. Every situation is going to be evaluated, all of them, and then all of the plus and minuses added up and tells you where you're at. Okay, so now we're going to do another one, which is basically optimizing chemical dosage. So in this case, what we're going to do is, first of all, we're going to take the number that we were just using and see if we can maybe make it a little bit more optimal than what we were spending. We're also going to look at the amount of polymer that we're dosing and what its cost is and how that affects the performance. And then also the flow split. So the splitting between going to landfill and going to land application after being digested. Okay, so what I'm going to do is I'm going to go from 1,500 down to 500 liters per day of dosing of the alkalinity correction. So I need to do a couple things here. First of all, I'm going to turn this off, and I'm going to go back to a different scenario. And I'm going to here we're going to hold that fog flow in the middle here somewhere. And I got more outputs set up for us over here. Okay, so now it's really this middle panel here that I want you to keep an eye on. Total chemical cost 388,000. And you can see below that here what some of our land applying and land filling costs are. Here's our stuff associated with the dewatering for land application and the dewatering for doing landfill. And you can see there's some high polymer dosage numbers here as well. Okay, so let's start out by reducing this down to 500. And then I'm going to rerun that steady state solution. And you can see this number came from 388,000 down to 316,000. And for the most part, these numbers are pretty similar. And our digester, here, let's put that back for a second. I meant to point out the pH before we made the change. pH before was 7.3. And then I'm going to put this at 500, our new optimal setting. And it's at 6.9. So basically what this tells us is we can make that reduction in chemical expenditure, and it doesn't really affect the performance of the place too much. So you can see on this graph, I realize it's a lot easier to see it on when I do it this way. So I'm going to show you the results on the slides rather than in GPS.X. Here, by changing this dosage, this blue is before the change and orange is after the change. You can see we reduced the cost by a fair bit. And you can see that it had negligible effect on the haulage issues, and our total cost has been reduced by this amount. So, all right, now we're going to do this again for a couple of more changes, and then I'll show you the total sum of all of it at the end. Okay, so now look at changing the polymer. So I'm going to leave this at the new dosage for our caustic, and I'm going to go to the dewatering, and I'm going to reduce these numbers here for the amount that we're dosing for the polymer. By quite a bit. So these numbers will come down here as well, and we'll see whether that causes us problems, because we might actually not dewater as well. So therefore we're going to pay more for hauling. And so I'm going to run that. And certainly these polymer costs came down, and these ones went up a little bit. And as I mentioned before, it's a little easier to see it as a bar graph. So I'm going to do that. Here's the numbers that we came up with by making those changes. And we can see we reduced, again, the cost down by quite a bit by reducing the amount of polymer we're dosing. And our actual costs of the disposal and the hauling did go up, but not nearly as much as this came down. So a net savings here. Okay, so last one is actually balancing the hauling and disposal costs between what gets landfilled and what gets land applied. So in this hypothetical example, we decided that the landfill was farther away than where the land application, like on a farm, for example, would be happening. So it costs more per meter cube to haul it to the landfill than it does to take it to the farm. We also had a much higher cost per ton to landfill than we did for land applying. So about half the cost to land apply. So clearly you can see land application is the better option of the two. So we want to try and optimize by moving to more land application if we can. So we're going to change the flow splitting. I'm going to leave that polymer dose where it was. We're going to go to flow splitting. And as our last action, I'm going to take, this is the one for the primary sludge. I'm going to take that up to 100%. We're going to move, rather than splitting it evenly, we're going to move the flow over to all of the primary sludge over to the digester. Now that of course means that we're now loading the digester quite a bit, and its SRT is going to go down, and we'll see whether that gain in gain in improvement in reduction in the amount that we have to landfill will offset that. Oh, I forgot to mention, in this particular example, we had decided to take the electricity out of the equation. We're saying, in this case, we're just flaring it off. We're not getting anything back from the increased gas. Okay, so I'm going to run that, and that's going to reduce these down again here. So our sludge hauling cost. So, and again, I'll show it to you as bar graphs instead, since it's much more straightforward. So now chemical cost didn't really change much, because of course, we're not changing the amount of chemical we're applying, other than the fact that less solids means less polymer for requirement. But we did get a net savings in haulage cost a little bit, and our disposal cost, because we moved some of the flow over to the other side. But At the same time, we still did okay with all of the rest of the production because we still managed to get the digester to do what it was doing. There was ample room in the digester to accept more of the solids over there, so that we could avoid the landfilling cost. It actually decreased the SRT from 20 to 16. This is getting on the low side, so maybe we don't want to push it any more than that. And this is how much we gained in terms of dollars for just this one change. So lastly, if I add up all three of those, this is what we did. We improved the chemical cost, we slightly improved the disposal cost, and overall here we cut the cost approximately in half. Now, that's a really extreme example. But what I wanted to do was to go through that process so that you could see and understand and get the feeling for the kinds of things that you can do with this type of analysis. There are many other things that we could have potentially done as parts of these examples. And if I had a whole afternoon with you folks, then maybe we'll do that. We have actually been talking about maybe making this into like a workshop. But nonetheless, sludge pretreatment, basically, if we put a THP unit in there, that's going to theoretically, hopefully, increase the biodegradability and increase the gas production. But then, of course, there's a cost associated with running it, so we'd have to balance that. Looking at side stream nutrient recovery, so there's some costs associated with doing that. You got to provide some magnesium, perhaps. Basically, you're going to get some revenue out of selling those nutrients, and so what balance does that have, and does that work for my particular plant and setup? And then lastly, changes in the influent. I mentioned way back at the beginning of the webinar that your sludge production is a function of many things, including your influent characterization. So if your influent has a huge amount of inerts, then you're getting a lot of sludge that doesn't have so much stuff that you can convert over to methane. So you're not going to see that same kind of feedback that you might see in some of the examples that we had here. Okay, so just to wind things up, as we're getting a little bit out of time here, the GPS.X Biosolids Handling section, those models can provide estimates not only of the performance of the treatment, but also how much energy was used, what the disposal costs will be with whatever's left over, and the potential energy and resource recovery options. So many of them have mass and heat balance models, and they're really good for sort of understanding, when you have a lot of options and you can move things around, how that's going to benefit you. And then lastly, again, simulation tools like sensitivity analysis work really well for this kind of thing. And so you can use this or the GPS.X optimizer to try and find the best place that you want to be with operating your facility.